Hello students, in today's lecture we are going to learn about motion in a straight line. NCERT Section 2.1 to 2.3. An example 2.1. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. So, in today's lecture, we will cover first introduction part, then instantaneous velocity and speed. After that, we will learn example 2.1 and 2.3 acceleration. So, introduction part. Objective: to understand motion exists everywhere in our universe. We know motion is common to everything in universe. How? We walk, run and ride bicycles. Even when we are sleeping, air moves into and out of our lungs and blood flows in arteries and veins. So we can say motion is common to everything in the universe. We see leaves falling from trees and water flowing down a dam. So this is also an example of motion. Automobiles and planes carry people from one place to other. The earth rotates once every 24 hours and revolves around the sun once a year. So this is also an example of a motion, or we can say motion is a common to everything in the universe. Yes or no? The sun itself is in motion in the Milky Way, which is again moving within its local group of galaxies. So these are the common things, or we can say common examples of motion. Now, here question arises, how we can define the motion. So basically, motion is change in position of an object with time. This phenomena is known as motion. To analyze and describe motion more precisely, we will introduce the concepts of velocity and acceleration. So, more about the velocity and acceleration we will learn in upcoming slides. We shall confine ourselves to study the motion of objects along a straight line known as rectilinear motion. So, here question arises, what is rectilinear motion? So, rectilinear motion is also we known as a straight line motion. So, suppose when we move on a single path, way, so this type of motion is a rectilinear motion, or we can say motion in a straight line. Motion in a straight line. Only in forward direction. So, suppose when we start moving from A position to B position, so in forward direction. So, this is a motion in a straight line, or also known as a rectilinear motion. I hope this is clear. For the case of rectilinear motion with uniform acceleration, a set of simple equations can be obtained. Finally, to understand the relative nature of motion, we introduce the concept of relative velocity. So, in our discussions, we should treat the objects in motion as a point objects. It means the size of object should be very small. That's why here we call points objects. We shall treat the objects in a motion as a point objects. Means size of object is a very small. This approximation is valid so far as the size of the object is much smaller than the distance it moves in a reasonable duration of time. Here, suppose the distance is very large. In that case, the size of the object should be point size. In a good number of situations in real life, the size of objects can be neglected and they can be considered as point-like objects without much error. Point-like objects means like a dot. So, this is a point-like objects. The size of object should be very small. That's why here we called points-like objects. In kinematics, we study ways to describe motion without going into the cause of motion. So, next is instantaneous velocity and speed. Objective: understanding motion involves analyzing speed and velocity parameters. Now, points here, points represent the size of object, or we can say size of object should be point size. So, positions of an object on a straight line path. Let's see. Suppose we have a straight line from O to A. The distance is 60 km. So, when we talk about a man, or we can say when an object moves from a O position to A position, so there is a change in position with respect to time. So, this phenomena we known as motion, or we can say this is rectilinear motion or motion in a straight line. So, our first case, rest. So, here question arises, what is rest? Suppose if a body does not change its position as time passes with respect to frame of reference, it is said to be at rest. It means a body does not change its position with time. So, we can say the speed of body should be equal to 0 if we talk about the condition rest. If we talk about the motion, so if a body changes its position as time passes with respect to frame of reference, it is said to be in motion. So, suppose we have a body at initial position at 5 km. After that, when time passes, the position will be changed. Suppose the position is 45 here. So, this is the change in position with respect to time, and this phenomena is known as motion. So, this is all about the rectilinear motion, or we can say motion in a straight line. Coordinates. Now here question arises, what is frame of reference? So, suppose we have a coordinates x, y axis, x axis and z axis. Similarly, second coordinates y prime, x prime and z prime. So frame of reference, it is a system to which a set of coordinates are attached and with reference to which observers describes any event. Rest and motion are relative terms. It depends upon the frame of reference. It means the motion depends on the frame of reference or observer. Speed. Now here question arises, how we can define the speed. So speed tells us how fast something is moving. It measures how much distance an object travels in a certain amount of time. So speed tells us the distance, traveling distance in a certain amount of time. So speed is a scalar quantity which has only magnitude and symbol is v. Dimension. So dimensional formula of speed is m0, l1 and t inverse. Unit meter per second in SI system, or in CGS system the unit is centimeter per second. Second is average speed. So how we can define the average speed? Thus average speed of a particle for a given interval of time is defined as the ratio of distance traveled to taken time, or we can say time taken. Mathematically it will be average speed is equal to distance traveled divided by time taken. So the average speed denoted by V average and distance traveled is delta S, whereas time taken is delta T. So using this relation we can calculate the average speed of a particle for a given time interval. Special case, and this is very important. When a particle moves with speed v1 up to half time of its total motion, and in rest time it is moving with speed v2. In that case the average speed, it will be v average is equal to v1 plus v2 divided by 2. So this is average speed if we talk about the special case. Clear? Instantaneous speed. So how we can define the instantaneous speed? So from the name, instantaneous means instant. So it is a speed of a particle at particular instant. When we say speed, it usually means instantaneous. So the instantaneous speed is average speed for infinitesimally small time interval, and that is delta t approaches 0. Thus instantaneous speed v is equal to limit delta t approaches 0, delta s divided by delta t, so is equal to ds upon. Now this is very important. So here instantaneous means particle at particular instant. So the time interval should be till delta t approaches 0. Delta t is not equal to 0 but approaches 0. Next is velocity. So the velocity is a vector quantity, or here question arises, how we can define the velocity? So the rate at which an object's position changes with respect to time, or rate of displacement per unit time, is called velocity. The common thing here between speed and velocity is the magnitude of speed. The magnitude of speed and the magnitude of velocity both will be same, because speed is a vector quantity, it has both magnitude and direction. So velocity includes both speed and direction of motion. So it has vector. The symbol is V with vector sign. So this is the symbol of velocity. And dimensional formula is m0 L1 T inverse. Unit meter per second in SI system. If we talk about in CGS system, centimeter per second. Clear? So this is the velocity, all about the velocity. Now, if we talk about the average velocity, so how we can define the average velocity? So average velocity tell us how fast an object has been moving over a given time interval, but does not tell us how fast it moves at different instants of time during that interval. So the velocity at an instant is defined as the limit of average velocity as the time interval delta t becomes infinitesimal small. In other words, v is equal to limit delta t approaches 0, delta x upon delta t is equal to dx upon dt. So this is the instantaneous velocity when delta t approaches 0. Here delta t is not equal to 0 but approaches to 0. It is very small. So v is equal to this one. And let this is equation 2.1, where the symbol limit delta t approaches 0 stands for operation of taking limit as delta t approaches 0, the quantity on its right. Here, this one. In the language of calculus, quantity on right hand side, look at here, dx upon dt of equation 2.1a is the differential coefficient of x with respect to time 2, time t, and denoted by dx upon dt. Clear? It is the rate of change of position with respect to time at that instant. So if we talk about the instantaneous velocity, so instantaneous means at a particular instant. So at a particular instant, the rate of change of position with respect to time is known as instant velocity. Or mathematically, we know v is equal to limit delta t approaches 0 dx delta x upon delta t, where limit delta t approaches 0 stands for operation of taking limit as delta t approaches 0. Clear? So this is the instantaneous velocity. We can use equation v is equal to dx upon dt, rate of change of position, for obtaining the value of velocity at an instant, either graphically or numerically. So here graphically or numerically is method to know about the velocity of particle, or we can say to calculate the velocity of particle. So suppose that we want to obtain graphically the value of velocity at time t equal to 4 seconds and point P for the motion of the car represented in figure below. So the time at time t equal to 4 seconds. So look at here, point P is this one. This is the point P. So at point P, the time t equal to 4 seconds. Here we will calculate the velocity of particle. So this is the graphical representation between position on y-axis and, or we can say, vertical axis, and time on x-axis, or we can say on horizontal axis. So here question arises, how we can calculate the velocity of particle at time t equal to 4 seconds using this graph. So here the slope of the tangent to the right of slope of the tangent. So this is graph, and the slope is slope of the tangent to the graph at that instant. 4 seconds gives us the velocity of particle. So let us take delta t equal to 2 seconds, centered at t equal to 4 seconds. So initial position is P1 and final position is here, suppose T, at t equal to 4 seconds. Then by definition of the average velocity, the slope of line P1, P2, slope of line P1, P2. P1 is this one and P2 is this. Slope of line P1, P2, look at figure, gives the value of average velocity over time interval 3 to 5 seconds. So when we calculate the slope of this tangent, so it gives the velocity. So position time graph. Look at here. We know P1, P2 is a straight line. So here we will calculate the velocity. Now we decrease the value of delta t from 2 seconds to 1 second. Then line P1, P2 becomes Q1, Q2. Q1, Q2. And its slope gives the value of average velocity over time interval 3.5 second to 4.5 second. So if we talk about the Q1, Q2. In the limit delta t approaches 0, the line P1, P2 becomes tangent to the position time curve at the point T. And the velocity at t equal to 4 seconds, it given by the slope of the tangent at that. So the slope of the tangent, this one. So for the graph shown in figure 2.1, x is equal to 0.08 t cube. Table 2.1 gives the value of delta x upon delta t calculated for delta t equals to 2.0 second and 1.0 second, 0.5 second, 0.1 second and 0.01 second, centered at t equal to 4.0 second. So look at table 2.1, limiting value of delta x upon delta t at t equal to 4 seconds. So the value of delta t is 2.0, 1.0, 0.5, 0.1 and 0.01 seconds. Similarly, T1, T2 and position at T1, position at T2 and delta x and delta x by delta t. So delta x upon delta t gives the velocity. So the second and third columns gives the value of T1. So how we can calculate T1? T minus delta t divided by 2. Similarly T2, t plus delta t by 2. And the fourth and fifth columns gives the corresponding value of x. So x t1 is equal to 0.08 t1 cube and x t2 0.08 t2. From this the value of x is obtaining from the graph. The sixth column lists difference of delta x, that is x of x of t2 minus x of t1, this one. And the last column gives the ratio of delta x upon delta t. That is the average velocity corresponding to the values of delta t listed in the first. Clear? So this is the average velocity from the graphically method. So we see from table 2.1 that we decrease the value of delta t, decrease the value of delta t from 2.0 second to 0.010 second. Look at here, from here to here. In that case, the value of average velocity approaches the limiting value, and that is 3.84 meter per second, which is the value of velocity at t equal to 4.0 second. So the value of delta dx upon dt at t equal to 4.0 second. Thus, we can calculate the velocity at each instant of the time for the motion of the. So here the important point is this: graphically method is not always convenient, or this is little bit tough for determining the instantaneous velocity. Clear? For this, we have to carefully plot the position time graph, and as delta t becomes small, then the value of average velocity has to be calculated if we have data of positions at different instants, or an exact uh, receive for positions as a function of time. Then the value of velocity at different instants is easy to calculate. Then we calculate delta x upon delta t from the data by subtracting the value of delta t and calculating dx upon dt, as we did in table 2.1, or by using derivative calculus for the given constant at different moments. Example 2.1. So this is important for understanding the concept of instantaneous velocity and and speed. The position of an object moving along x-axis is given by x is equal to a plus bt square. So position is given. Listen carefully. Position is given, where a is equal to 8.5 meter and b is equal to 2.5 meter per second, and t is measured in seconds. Is the time measured in seconds. What is its velocity at t equal to 0 second and t equal to 2.0 second? And what is the average velocity between t equal to 2.0 second to and t is equal to 4.0 second? So here we have to calculate the velocity at given instant and average velocity. Clear? So in notation of differential calculus, the velocity is, the notation of differential calculus, v is equal to dx upon dt, dx upon dt. So here x is given, so just calculate the derivative of x. So it will be d upon dt, the value of x a plus bt square. So here is a constant, so the derivative of constant is 0, the remaining term is bt square. So b comes outside, t square, so t comes outside and minus 1, so 2 minus 1 will be t, so 2b t, or we know the value of b, that is given 2.5 meter per second square. So 2.5 into 2, it will be 5, so 5t meter per second. So this is the velocity from the differential calculus. At t equal to 0 second, v is equal to 0 meter per second. And at t equal to 2.0 second, v is equal to 10 meter per second. How? So just substitute the value of t here and you will get the velocity. Average velocity. So x into 4.0 minus x into 2.0 and divide by time interval. So 4.0 minus 2.0. So after calculating it, you will be get a plus 16b minus a minus 4b divided by 2. So it is equal to 6 into b is equal to the value of b, substitute here. 6 into 2.5 is equal to 15 meter per second. So here 15 meter per second is the velocity, or we can say average velocity. So question asked about the velocity at t equal to 0 second and t equal to 2.0 second. So if we talk about that at t equal to 0 second, the velocity is 0 meter per second. And if we talk about the at t equal to 2.0 second, the velocity is 10 meter per second. So this is our first case. If we talk about the second case, average velocity, and the time interval is this one. So in that case, the average velocity is 15 meter per second. I hope this is clear. The important point here is, note that for uniform motion, velocity is same as the average velocity at all instants. Instantaneous speed, or simply speed, is the magnitude of velocity. For example, the velocity of 24.0 meter per second and a velocity minus 24.0 meter per second. Here, this shows the in positive direction and here minus. Both have associated with speed 20.0 meter per second. So here, look at here. If we talk about the plus 24.0 meter per second, so this is the velocity and magnitude is 24.0 meter per second. So here minus 24.0 meter per second, velocity is this one and magnitude is 24.0 meter per second. Clear? It should be noted that so average speed over a finite interval of time is greater or equal to magnitude of average velocity. Instantaneous speed at an instant is equal to magnitude of instantaneous velocity at that instant. So this is important. Next is acceleration. Objective: understanding acceleration involves changes in velocities rate. Now here question arises, how we can define the acceleration. So basically the acceleration is the time rate of change of velocity of an object is called acceleration of the object. It is a vector quantity, means it has both magnitude and direction. Its direction is same as that of change in velocity, not for velocity, not of the velocity. Dimension formula: m0 l1 t raised to the power minus 2. Unit: meter per second square in SI system. If we talk about in CGS system, the unit is centimeter per second. Clear? So this is the acceleration, rate of change of velocity of an object. Now there is a two type of acceleration. First is uniform acceleration, second is non-uniform acceleration. So if we talk about the uniform acceleration, a body is said to have uniform acceleration. The condition is if the magnitude and direction of the acceleration remains constant during particle motion. So this is the uniform acceleration. Magnitude and direction of acceleration remains constant during given time. If a particle is moving with uniform acceleration, this does not necessarily imply that particle is moving in a straight line. Example, projectile motion. Projectile motion is a two-dimensional motion, or we can say motion in a plane. So more about the projectile motion we will learn in next chapter. The second type of acceleration is non-uniform acceleration. So if we talk about the non-uniform acceleration, a body is said to have non-uniform acceleration if magnitude or direction of both change during motion. Means the magnitude or direction or both change during the motion. That type of acceleration is non-uniform acceleration. Clear? Average acceleration. So if we want to calculate the average acceleration, so delta v divided by delta t. Delta v is change in velocity. So v2 minus v1 and delta t is time. So using this formula, we can calculate the average acceleration, or we can say it gives us average. The direction of average acceleration vector is the direction of change in velocity vector as a is equal to delta v divided by delta. Instantaneous acceleration. So if we talk about the instantaneous acceleration, instantaneous means at a particular instant. So limit delta t approaches 0, delta v upon delta t gives the instantaneous acceleration, or we can say dv upon. Clear? The acceleration at an instant is the slope of the tangent to vt curve at that. For a moving body, there is a no relation between the direction of instantaneous velocity and direction of acceleration. This is only for a moving body. Example, in a non-circular motion, in a uniform circular motion, if we talk about the uniform circular motion, theta is equal to 90 degree always, and b is in a projectile motion, theta is a variable for every point of trajectory. Because in projectile motion, it make the projectile trajectory. So theta is a variable in that case. By definition, a is equal to dv upon dt. So here dv upon dt is equal to dx square upon dt square. So we know v is equal to dx upon dt. That's why here it will become dx square upon dt. If velocity is given as a function of position, then by chain rule, a is equal to dv upon dt, we know. So dv upon dx into dx upon dt. So this is same as dv upon dt. So dv upon dx and dx upon dt. So we know dx upon dt is velocity. So here it will become v into dv upon dx. If a particle is accelerated for a time t1 by acceleration a1 and time t2 by acceleration a2, then average acceleration is this one, a1 t1 plus a2 t2 divided by t1 plus t. So this is the average acceleration. Acceleration can be positive, 0 or negative. Positive acceleration means velocity increasing with time. Zero acceleration means velocity is uniform constant, while negative acceleration means retardation, or we can say velocity is decreasing with time. Clear? For motion of body under gravity, acceleration will be equal to g. where g is acceleration due to gravity, and its normal value is 9.8 meter per second square, or 980 centimeter per second square. So this is the acceleration. Since velocity is a quantity having both magnitude and direction, a change in velocity may involve either or both of these factors. So acceleration, therefore, may result from a change in speed, means magnitude, a change in direction, or changes in both. Like velocity, acceleration can also be positive, negative, or zero. Position time graph. Look at here. A, B, C. So here A represents positive acceleration. B represents negative acceleration. And C represents zero acceleration. Constant velocity. The position time graphs for a motion with positive, negative, and zero acceleration are shown in figure A, B, and C respectively. Position time graphs. So we know A is positive acceleration, B is negative acceleration, and C represents zero acceleration. Note that the graph curves upward for positive acceleration. Upward for positive acceleration. And this one for downward, this one negative acceleration. And a straight line is zero acceleration. Although acceleration can vary with time, our study in this chapter will be restricted to motion with constant acceleration. So in that case, the average acceleration equals the constant value of acceleration during the interval. If the velocity of an object v naught at t equal to 0 and v at time t, so acceleration is equal to this v minus v naught divided by t minus 0. The equation become v is equal to v naught plus, let this is equation 2.4. So this is equation of motion. V is equal to v naught plus at. Let us see how velocity time graph looks like for a simple cases. Figure 2.3 shows the velocity time graphs for motion with constant acceleration for following cases. So first case, an object is moving in positive direction with positive direction. Look at here. On y-axis, or we can say vertical axis, velocity, and x-axis, time. Here, objects moving in positive direction. So here, look, positive direction, yes, with constant velocity. Acceleration is positive. B is an object is moving in positive direction with negative acceleration. Look at here. Object moving in positive direction. This quadrant is positive direction with negative acceleration because velocity is decreasing. C, third case, an object is moving in negative direction with negative acceleration. Here, in negative direction, this one with negative acceleration because the quadrant is negative and velocity is also decreasing. D, an object is moving with positive direction till time t1 and then turns back with same negative acceleration. Look at it. D graph. Negative at t1 from negative. First, in first case, direction is positive, but acceleration is negative. But after t1, the acceleration is negative. We can, however, see that it is a true for simple case of an object moving with constant velocity u. Velocity time graph is shown in figure. So this is velocity time graph. So area under velocity time graph equals to displacement of object over a given time interval 0 to area under VT curve equals to displacement of the object over a given time interval. So VT curves in a straight line parallel to time axis, parallel to time axis, and the area under the it t equal to 0 to t equal to t is the area of rectangle of height u and base t. So the area is u into t. So ut, which is displacement in the time interval. Clear? So this is the area under method to calculate the area using VT graph. I hope this is clear. Thank you for your attention.